Have you ever been driving at night and look into the dark night sky and ask, is there anyone else out there? Looking up and seeing all of these stars that are trillions of miles away, some brighter than others, and seeing familiar ones like the Big Dipper, Polaris, and so on. It makes you wonder which, if any of these distant stars could harbor life. This one maybe? How about this one? That one possibly? Only if there were a way to figure out how much, if any, life is out there. The thing is, we can, thanks to Drake. Well, not that Drake. Dr. Frank Drake. Dr. Drake, who was an American astrophysicist and astrobiologist, started out as a radio astronomer. After some time, his interest in extraterrestrial life led him to begin Project Ozma in 1960, in which he looked for radio signals from nearby star systems. This project ended in the middle of that year due to lack of results, sadly. Drake is also well known for his lifelong collaboration with the esteemed Carl Sagan. Drake and Sagan worked together to create the famous Pioneer plaque, which was placed onto 2 space probes, which was the first physical message sent into space intended to be understandable by intelligent extraterrestrial life. Before his work on the Pioneer plaque and collaboration with Sagan, he created Drake's equation in 1961. This equation that Drake made is to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. The equation is as follows: N being the number of communicative extraterrestrial civilizations in the Milky Way, R star being the average rate of star formation in our galaxy, times Fp, the fraction of those stars which have planets, times Ne, the average number of planets that can potentially support life per star that has planets, times Fl, the fraction of planets that could support life that actually develop life at some point, times Fi, the fraction of planets with life that go on to develop intelligent life, i.e. civilizations, at some point, times Fc, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space, whether it be objects such as ships or probes, or signals such as radio waves like we send out and scan for, times L, which is the length of time at which such civilizations release the detectable signals. This equation has been used for the past half-century to estimate how much intelligent life is out in the Milky Way. Although there are some criticisms and critiques of the equation, I'll address those later. Now that we know what the Drake equation is, I would like for us to make our own estimate to answer the question of if there is life out there, how much life is there? Starting with our star, it is a fairly straightforward variable. The rate of star formation in the Milky Way is calculated anywhere from 1 to 10 solar masses per year. Most current estimates are around 2.5 solar masses per year, although this is my estimate and I would like to go more on the generous side for this variable and choose 5 solar masses per year. Next, we have Fp, the number of stars which have planets. There are different kinds of stars, with them being classified by their spectral characteristics, which give information about their size and temperature. These classes are M, K, G, F, A, B, and O. Most stars with planets, though, are F, K, and G classes, with G class being the most important to us because our Sun is a G-class star. For simplicity, let's consider that only these star classes have planets, while the other classes have none. If we are considering that these 3 classes contain all of the planets, then it could be said that 3/7, or roughly 43% of stars have planets. The issue with this estimate is that star classes do not contribute equally to the total quantity of stars. F-class stars make up 3% of all stars, with G-class making up 7.6% and K-class stars making up 12.1%. If we add these 3 percentages up, we get 22.7%, or 0.227 of the fraction of planets with stars. Going forward in the equation, the variables become more speculative and estimated. Next we have Ne, the number of planets that can support life. As a prerequisite, before we continue, we should go over the requirements of life to exist on a planet. 2 main things being that it is a rocky planet, as gaseous planets cannot sustain life, and B, being that it contains liquid water. On average, stars that have planets have 5 to 10 rocky planets. Our Sun is close to the average, with our solar system having 4 rocky-bodied planets in total. The first and most important, Earth, followed by Mars, Venus, and last but not least, Mercury. For our solar system example, I would say 2 of the 4 planets are capable of supporting life. Earth, as everyone hopefully knows, is where we are and is very capable of supporting life. Mars is the second planet that I would consider capable of supporting life. Mars has been speculated to support life, as it has been known that frozen and liquid water is present on the red planet. As time goes on, there is more evidence support that it can sustain life. Most recently, a study came out that used models to show that there's enough light that can penetrate meters-thick ice to support photosynthesis in the water beneath. This ice shield also protects from the lack of atmosphere and harmful radiation from the sun. With this information on Mars, I would say it is easy to count it as a planet that can support life in our solar system. Further, for liquid water to be present on the planet's surface, it would have to be in the Goldilocks zone. This being the range from its sun, where water, for at the most part, remains liquid on its surface. The Earth is in our Goldilocks zone, and it's possible that in Mars's past, it was capable of supporting liquid water on its surface. In this example, the red planet's orbit remains in the Goldilocks zone, where the green and pink planet's orbits do not. Although being in the Goldilocks zone may not be a requirement to sustain life, as there are some cases that may extend out of the zone due to special circumstances, I will get to that after the finalization of the estimate. Getting back on track, with our solar system having 2 rocky planets out of 4 that can sustain life, I will take half of the lower estimate of 5 rocky bodies, getting 2.5 planets per star that can sustain life. Following NE, we have FL, the fraction of those planets that can sustain life that actually develop life. If I estimated that 2.5 planets can support life, the minimum number of planets I would estimate is that 1 out of the 2.5 planets has life, making the fraction 0.4. And on the higher end, I would estimate that 2 planets maximum out of the 2.5 have life, making it 0.8. To meet in the middle between the two, I would estimate that 0.6 or 60% of the number of planets that can sustain life actually develop life at some point. Next we have Fi, the fraction of planets with life that develop intelligent life and civilizations. Although this is completely a guess, I will say that there's roughly a 50-50 chance that life becomes intelligent, and that we just happen to fall in the lucky half. Getting close to the end now, we have FC, the fraction of those intelligent civilizations that release detectable signals of their existence. This is one of the few variables that I will agree with Drake on from his original estimate, and say that 1, or there being a 100% chance that if a civilization comes about, that eventually they will become advanced enough to release signs of their existence. The main reason I think that this variable is correct is that we are the prime and only example where a civilization leads to releasing signals of their existence, and that we have no other examples to compare on a planetary level. You can make an argument that other species of humans, such as Denisovans or Neanderthals, count as intelligent life that did not go on to make signs of their existence, making the fraction closer to 1/3. Although they had similar intelligence levels and also had similar forms of social and ritual acts, I would not consider them to have had civilizations. Last but not least, we have L, or the length of time those detectable signals are released for. This value, like the past few, is mostly a guess, as we have only been releasing detectable signals for 100 years if we round up. There is no way of knowing how long humans as a civilization will continue to do so. My only guess is to just use the value of how long modern humans have been around for in total. So, from the times of prehistory to recorded history to the modern day is anywhere from about 40,000 to 100,000 years. Further, I think it is fair to say that if another distant civilization became capable of sending detectable signals, maybe they could be able to settle their differences and not threaten mutually assured destruction every 50 years or so. Now, to plug all of our values into Drake's equation. An R star of 5 stars per year, FP of 22.7% or 0.227 of stars that have planets, and E of 2.5 planets per star capable of developing life, FL of 0.6 in that 60% of stars that can develop life do, Fi of 0.5 or 50% of life that comes about becomes intelligent and forms civilizations, FC of 1 in that all life that develops civilizations will release detectable signals of their existence, and an L of 40,000 years being the length that they release those signals. And if we multiply all of those values, we get 34,050 of those signal-sending advanced civilizations. Now, if we were going to plug in the higher end of L of 100,000 years for the length of time that they release signals, then we get 85,125. With our estimate, there are 34 to 85,000 civilizations currently that we should be able to detect at some point. Although this number may seem high at a first glance, it is tame in comparison to the high end of Drake's original estimate of 50 million in 1961. Although, this is just my rough estimate. If you want to go ahead and make your own estimates with Drake's equation in the comment section below. There is no right answer, all are just estimated guesses. That is one of the critiques I will now address about the equation. As I just mentioned, the main critiques are the unreliable nature of the estimate. As the variables can vary widely, the estimation as a whole has been called meaningless by some. Other than that, the actual variables that are used are based on conjecture. Later variables in the equation, like Ne, Fl, and Fi, are possibly in reality close to zero in value, but there's just no way to figure that out, as we are the only example of life that is intelligent and sends detectable signals. One critique I had that I did not see in my research is that in this equation it does not include other extraterrestrial bodies such as moons in the equation. The main reason I thought of this is that, other than Mars, there is another potential harbinger of life in our solar system, Europa. Europa is a moon of Jupiter and is well outside of the Goldilocks zone. Its surface is covered in a miles-deep layer of frozen water, but the rest of the planet is estimated to be mostly liquid above the crust, containing more liquid water than on Earth. Due to this moon, outside of the Goldilocks zone, being able to sustain and possibly have life, I think that both moons and planets should be considered in the equation, which would increase the value of Ne. So, that is Drake's equation and my estimate for how many signal-sending extraterrestrial civilizations there are. Thank you all for watching this far. Please like and subscribe if you're interested in seeing more content like this. As mentioned previously, I'm interested in any of your estimates if you wanted to give it a go in the comment section below. I appreciate all the support I've received in making this from friends and family, and I'll see you in the next one.